Hey everyone, welcome to the language theory problem section. This lesson we are going to solve the problem 5 of this section. This problem 5 says, argue whether the following general statement is true with a justification or false with a counterexample. Right, so this is here the statement, okay, that we have. So essentially what this is saying is that if I have a language, L1, and I apply the cleans closure operation to this language, and I concatenate this language L1 with another language, L2, also applying the cleans closure, this language here, this resulting language is a sublanguage, okay, it is a subset of this language in here, which is the result of first concatenating both of these languages and then applying the cleans closure. So here we need to justify if this is true, and in the case if this statement is false, in general, there are certain situations and cases where this is not satisfied, we need to give a counterexample. So to solve this problem, I want you to think of these two languages as follows. Suppose the language L1 is the language A, consisting of only here the terminal symbol A, and the language 2 is the language that only has the terminal symbol B. So now let's try to apply the cleans closure to both of these languages. First, we apply this cleans closure to the language 1. We already saw this operation, right? Remember, this is the language that represents all the combinations that we can form with this terminal symbol. So essentially words that will belong to this language, okay, with the cleans closure, will be, for instance, the word A, the word AA 2 times the terminal symbol A, the word AAA 3 times the terminal symbol A. Also, the empty word is a word that belongs to this language, since with the cleans closure we can apply 0 or more concatenation of this terminal symbol, right? And we will have here lots of possible combinations, each one with a total size of 1, okay, more than the other, which is the previous one. As we can see, this has size 2, 1 more than the previous one, this has size 3, 1 more than previous one, and so on. Now the same idea if we apply the L2, okay, with the B. But first let's formalize this cleans closure, okay, with the language L1. So we can formalize this language in the following way. This language here represents all of the combinations a to the power of n, such that n is greater or equal to 0. Okay, keep in mind that when the n is 0, we have this case, we have the empty word lambda. When the a is 1, then we have this case, right, and so on. This is also the same as writing here the cleans closure of this language A, and also the same as applying the cleans closure to the terminal symbol A, since this language has only one terminal symbol. Very well, now we do the same thing with the language 2 that has the terminal symbol B. So now the language 2 here, if we apply the cleans closure into this language, again, what this represents now is the language empty word, B, BB, D, BB, and so on. Right? So here we have all the possible combinations with the terminal symbol B, so B raised to the power of n, such that the n is again greater or equal to 0. This is the definition of the cleans closure applied to a language with only one terminal symbol, right? This is the same as here applying the cleans closure to this language B, which is the same as applying the cleans closure to only this terminal symbol B. Very well, now with this assumption and with this reminder of the cleans closure and also with these formalizations, okay, we can see now if this is true or false, what this statement is saying on this problem. Now let's see here and let's verify if this is really a subset or a sublanguage of this one. So what if we try first to concatenate both of these languages and then applying this cleans closure operation? Now remember, if now we have a concatenation, this concatenation can be represented with here this dot, or you can just leave nothing. Both of these ways represent a concatenation. Right? We are going to explicitly here represent this dot. So now we are making now the cleans closure of this language. And this language is the concatenation of A and B. So now we can formalize this, okay, applying the cleans closure as the language that has always AB, okay, in parentheses, raised to a given value, k, for instance, such that this value k, this exponent, is greater or equal to 0, by definition of the cleans closure, right? Like this. So now if we see this, okay, and we evaluate this, of course, this language, okay, will contain words, okay, different from the previous language. And not only that, it may happen that this concatenation, which is this first concatenation that we saw, this new resulting language has words also that do not belong to this language in here. So let's prove this, because this is not a true statement in general, this is false. So let's give a counterexample. It is very simple to see. Just consider this word, the word A, B. Okay, just imagine this word. This is a word that belongs to the first here resulting language, right? The language on the left, this one in here. This is a word that belongs it because, as we can see, this value here, AA, right, comes from this language in here, and we are concatenating this word with this one. Just a simple concatenation, okay? By definition of this concatenation here. So we take a word that belongs to this language, we concatenate this with a word that belongs to this language, therefore this word in here will belong to the concatenation of these two languages. Now, does this word AABB belong to this language in here? And the answer is no. It doesn't belong, because this language only contains words that start AB. Okay, so essentially we can represent this language in here, just on the top, okay, as words in this kind. We can have the word, for instance, empty word, because we have here the possibility that k is 0, by definition of the cleans closure. And then we have, what if the k is 1? If the k is 1, we have AB, right? One occurrence of AB. If the k is 2, we have 2 times this occurrence AB. So we have AB, AB. What if the k is 3? We have AB, 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 and so on, okay? Therefore, there will never be a word such like this one, AAB, inside this language in here. So we can conclude that this word, okay, belongs to this language in here, this resulting language, and also this word, AAB, doesn't belong to this language in here, which is the resulting language on the right of our statement in this problem. So L1 concatenated with L2, and all this in parentheses made the cleans closure, like this. So very important to understand this. We have arrived to a point that we here encountered a word that belongs to this language and doesn't belong to this language in here. Therefore, there's no way that this language can be a sublanguage to this one. Because if this language was a sublanguage, all of the words, okay, that contains this language, also here, this language must contain them, right? All of the words that belong to this language, that are inside to this language, must be inside and must belong to this resulting language in here. But this is not the case. We have just found a counterexample. The word AAB belongs to this language, to this resulting language, and this same word AAB does not belong to this language. Therefore, this statement is false, and we have given this counterexample. With this, we end the solution to this problem 5.